I'm going to walk through a problem that's found on the APMonitor.com website. If you go down to the process control course and then select homework and then scroll down a little bit, you'll see special problem 3. This is a dual gravity drain tank, and I'm going to use a first order plus dead time model to fit this dynamic data and then tune a PID controller, actually a proportional only controller for this tank. And so we're going to go through parts 1, 2, and 3 for this. I'll just go ahead and leave this open as we go through it. And the first thing that we need to do is go and get the Excel and Simulink files. So I'll go ahead and download those. Okay, so once they finish downloading, then I'll extract them. And so just extract. I'll just extract to my desktop. And so there are the files. I'll go ahead and close the zip file. And I have two things in this folder. I have the Tank Simulink and then also the first order plus dead time gravity drain tank worksheet that helps you fit some of those parameters. So first of all, I'm going to go into the Tank Simulink and then go ahead and open up this gravity drain tanks, the SLX, the Simulink model. And one of the things to remember is if you're using the RGS server or Citrix to use MATLAB, is you want to make sure that when you open it that you're in the correct directory of that folder. Otherwise it's not going to be able to find some of the files that it needs. Okay, so just make sure that is correct before you open up the this Simulink model. Okay, so it's open now. I'm going to go ahead and go to my gravity drain tank model, and what I'll do is go ahead and just run it first of all, just to go ahead and generate a step response. So what I'm going to do is go ahead and click run. Okay, and then what's going to happen is a tank schematic is going to appear here. Then it'll also open up pump output. It's going to open up a slider box that is going to allow me to adjust the pump output. So what I'm going to do is go ahead and just do a step to about 50%, about 49 in that case, and then I'm going to watch the values increase. I can view as I'm waiting for this to come up. I can look at the measured levels. So let me bring over that plot. I can see these traveling up. I want to wait till it gets to a steady state, and then I'll go ahead and determine what a probable model would be just using a graphical method, and then we can also we can also use an optimization method that's going to be in Excel. Okay, so you see this coming up. This is the height, the second tank that I'm interested in, and you can see the first tank value. It's leveling off. It's going to get to about 500 seconds of simulation. You can see the progress right down here. It's 93% of the way, and it's going to finish right about now. Okay, so I see a plot that appeared as well right after I finished, and you can see the pump output. It went from right at about 100 seconds, it went up to about 0.49, and then you can see level 1 and then level 2. So what I'm going to do is go ahead and just make this a little bit bigger so I can see, try to pick that out graphically. What is my I'll move that legend out of the way. Okay, so you can see here it's very minimal dead time. If I drew a tangent down, it would, very little delay between when the step occurred and when you see the initial response. And then the first thing we need to do is determine what is the, so I'm going to do my little tracer tool here. So right at the top there's a little data cursor. And if I go ahead and select, I can see the actual value. So what I'm going to do is go ahead and trace it, along this this plot here, and just kind of figure out what the final steady state value appeared to be. It looks like it was still going up just a little bit. Let's just say it's 0.68. Okay, so what we need to do now is we've got a change of 0.68. That's my delta y, and my delta u, my input, was about 0.5. Okay, so my gain in this case, my gain is delta y divided by delta x, or sorry, delta y divided by delta u, the input, and so I've got about a let's just say a 0.7 divided by 0.5, so a gain of about 1.4. Okay, so that's my gain is 1.4. I'm just going to go ahead and record that here. Let me go ahead and just get a new text file here. Okay, so my gain, that's going to be my KP, is going to equal about 1.4. And Now I need my time constant as well. Let's go ahead and look for, actually the first thing we need before time constant, we always need to do the dead time, okay, before the time constant. We said that was very low. It might have been, you know, just minimal, maybe 1 second dead time. Time constant, let's go take a look at that right here. So 63% of the way there. Let me go ahead and just open up my calculator. I'll go ahead and open up Excel. And let's just do our 0, it was about 0.7 times, okay, so 0.632. Okay, so I need to look for where this got to about 0.44. Okay, that's going to determine where my my 1 tau, so 0.44, somewhere right around here, 232 seconds, and it started right around 108. Okay, so 232 minus 108. Okay, so let me go ahead and just write that in my my notepad here. 232 minus 108. Okay, so that is going to be let's see, that's going to be 124. Okay, so 124 seconds. Let's go ahead and put the units in here. You know, this is a fractional change in level divided by a fractional change in pump output. This one's actually going to be unitless for now. We want to go ahead and make sure we get the right units. The dead time, that's also going to have units of time, and this one is seconds. Okay, so we're going to have, and I'll call this one tau p, and then this one, sorry, this one is tau p, and then this one is theta p. Okay, so we have theta, the dead time, and then tau p, the time constant for our system. Okay, so so we've got these, and that was the graphical method. What I'm going to do now is go ahead and get that data out, and also fit with optimization techniques the same 3 parameters. Okay, so let me grab my data. If I go back to my run directory here, it saved a file for me. It saved a, go ahead and minimize that and get back to my directory right here. It saved datamanual.txt, and if I open it up, I can see, you know, a bit of data here. You got to go back to the Simulink plot and figure out what all of these columns are for this data file. But let's go ahead and do that. I'll just walk through the Simulink file for this gravity drain tank problem. So we had a set point. This is just going here into save into the manual.mat, the mat file that's a native file in MATLAB, and then it's saved at the end of the routine as a .txt file. Okay, so the very first thing is actually time. It'll save time in here, and then the second thing is going to be the set point. Okay, the set point, and this is going to be 0.5. So let's go ahead and open that back up again and just confirm that that's our second thing that we have in this data file. So it's time and then 0.5. Okay, so let's look at what's coming in next. This MUX or MUX, that'll go ahead and combine the values. Okay, so I had the top one, that's my set point, and then this one is coming out of here. Now this is the valve position and also pump output. These are combined, and then it goes into the second one. Okay, so I have my pump output, which is going to be this is the valve position, and then pump output is the 4th column. Okay, so let's look at what we have for the 5th and 6th columns. It's coming out of the tank dynamics. Okay, so this is the height 1 and height 2 for my tank 1 and tank 2. That's coming in here. So there's height 1 and height 2. This is the variable that I'm going to be trying to control, and this is the variable that I can manipulate with the PID controller. Okay, so let's go ahead and just copy that out. Okay, I'm going to go ahead and copy this, and just go ahead and do a Control-C, copy it, or you can come to up here and do a copy command. And then what I'm going to do is go ahead and open up the Excel spreadsheet that came with this. Go ahead and click Enable Editing to be able to start. So what this does is you need to insert the input U, which is in this case it's going to be that pump value, the fourth column, and then also input the measured value. This is just fake data right here. It's from a different process, but we're going to try to optimize the gain, tau, and theta in this using the Excel solver. Okay, so what I'm going to do is go ahead and have some results. Let me go ahead and just make a new sheet and just go ahead and paste that in, and then let me see, data, and then text to columns, and I'm going to say it has a fixed width, and I'll finish there. Okay, so what I want to do now is go ahead and take my time. Okay, I have my time right here. It went up to 500 simulation seconds, and I'll go ahead and paste that here on the okay, so there are my seconds. It went down a little bit further than than my other columns, so I need to fill those down. Okay, let me go get my input. Okay, so I need to fill in my input. That was my fourth column here, and go back to data and go ahead and put in my input. Okay, and then go ahead and copy this final one. We're going to be able to predict the Y model. You can just leave this equation alone if you like. It'll go ahead and you may need to fill it down a little bit more just to I'll show you how to do that. But now we need to get the measured value as well. So let me go get this this last column. Okay, so go here and paste the measured value as well. Okay, so let me go ahead and copy this one down. If you just go ahead and double click on this little black box, it'll go ahead and fill down for you. I'm just using the control key. Hold the control key and push up, and it'll go to the top. Control key and push down, and it'll go down to the bottom. Okay, so now I want to look at these as well. I have absolute error and then also error squared. So we're going to do a summation of the errors and try to minimize that. Okay, so it's going to try to minimize the difference between the model and the measured values by adjusting these three parameters that we have on this side. Okay, so that is a correct formula here to be able to do the absolute value. Now I always have a hard time getting out of here without changing the formula. Okay, I'm gonna scroll down, and then I'm gonna highlight both of these. Just go ahead and fill down the sum of squared errors and sum of absolute errors. Let me just go ahead and make sure that this covers the appropriate range. So it goes up to 5,000. That's more than enough. It only went for 500 time steps, and then this one as well went for 5,000. Okay, so I see a difference here between my model and my measured value, and then you can see also the plot for the manipulated variable, the step that I had in the pump output. Okay, so this sheet is already configured. You just have to paste in the data, and then let me just go ahead and change some of these. Let's just change them to our ones that we obtained from the graphical fit. You don't have to do this. You can go ahead and optimize it if you want. I think we had about a 1.4, and then our time constant was 124. Okay, so there is my fit that I obtained from my graphical method versus the actual measured value. Let me go ahead and optimize this now. Let's go ahead and just optimize this by using the Excel solver. If you don't have this, you may have to go to your add-ins and add it. Let me just show you how to do that if I can figure that out. I always forget how to do that. I think it's here in add-ins under File and maybe Options. Yeah, there it is. Okay, under Options, and then if you go down to Add-ins, you'll be able to see the different add-ins that you can add. You may need to add the Excel solver to be able to use it here. Okay, so what I'm going to do is go ahead and go back to Data, and I'll click on Solver, and then set my objective. So I can either do the sum of absolute errors or the sum of squared errors. So I'm just going to go ahead and do the absolute errors instead of the squared errors, and then I'm going to be able to change these three values. Actually, the program that I have set up right here doesn't do the time delay for you, and so it doesn't really change anything in the model. Go ahead and just do these for now. The time delay is pretty minimal with this one. I'm still trying to think about how to add that theta value and be able to estimate it within Excel. It seems like it's going to be a little bit more difficult to program than I originally imagined. Go ahead and click Solve here, and let's just see what it came up with using an optimized solution. So you can see maybe just a little bit better fit here. And you can see that the time constant we had estimated 124 and then a 1.4. So these are just a little bit better gain in time constant. So I'm just going to change that to any value right now, 5 and 0.1. Just see if we can get back there again. So if I click Solve, okay, it still gets back there. So you really don't need to put too good of an initial guess in there. It'll be able to find it for you. Okay, so I have these parameters. Let me just go ahead and copy these out and go ahead and put them into my notes here. So with optimization, I got KP equals that, and then tau P equals 126, and then theta P, you know, it's I guess 0 seconds. We didn't try to estimate it. Let me go ahead and put the time units there as well. Okay, so that is unitless. Okay, so let's go ahead and get some, go ahead and do a doublet test for our model as well. I'll go back to the MATLAB. Okay, go back to the gravity drain tank. So what we're going to be doing is just changing this pump output. I'm going to first of all just set it to 0. Okay, just to start, and then we'll go ahead and do a doublet. I'm going to go a little bit longer time, maybe 1,000 seconds here, just because I don't think it's going to make it to steady state. We don't need to let it get all the way to steady state when doing a doublet, but we just want to be able to sample from different regions. So I'll go ahead and run it. Okay, so you see that the tank is not filling. I'll go ahead and set the pump output. Let me go ahead and just go to 0.5. Okay, and then let's look at these measured levels as they're coming up. Okay, so if I just click this button, it'll rescale, and I can see the tank filling up. I need to do everything before 1,000 seconds because that's when the simulation is going to stop. Okay, so I'm about to I'm getting close to steady state. Let me go ahead and do my step up. Okay, so I'll do a step up, and I don't want to overfill this tank, so I got to be careful here. Ooh, I did. Okay, there it is. I'm going to do my step down, and that may cause just a little bit of a problem with the fit. We'll just see. I overfilled that first tank, and okay, so there is my step down. Okay, this is not a very good doublet test. I think I went too high on the upper one. If I did it again, I'd go a little bit lower and wouldn't overfill that one. Okay, so it almost completely drained there, and for 1 and 2, and now I'm going to go back to my nominal value. So a doublet test, you go up and then down and then back up to its nominal value again, and you get the response. Okay, so we've done that here for this this gravity drain tank. Let me just go ahead and look at the tank as it's filling up. When we get to the controller, we're going to try to have this control right here to this set point. This is the set point level for our tank. Right now we're in manual mode, but we'll be adding a PID controller. Okay, so we'll just let this get to steady state. Now in the doublet test, there isn't any prescribed value. You just want to be able to sample up and down, kind of in regions where you think this this problem is going to be nonlinear. You want to be able to go ahead and sample in multiple regions to be able to determine if the system is nonlinear, and to be able to get a good approximation for these values over a wide range. Okay, so it's almost done. I'm getting a little bit tired of waiting here. You can stop it if you want to. You don't have to wait till it's done. And I'll just go ahead and stop it here. It'll generate the plot, and you can see my doublet test. It went up and then down and then back up to its nominal value. You can see on the first tank I overfilled here on tank 1, but then went down and then back up again. Okay, and then you can see the same thing happen here on level 2. Okay, so let's go ahead and take this data now, and we'll fit that and just compare it to what we got with the step test. Okay, so I'm going to go ahead and minimize this, go back here. I'm going to put my data back in here. Okay, so I'll go ahead and reload my data. It created a new data manual.txt file. I'll go ahead and just select this and then add it to my gravity drain tank. I'll just create a new sheet with this new data and just do my text columns again. And if you remember, our fourth one was the control input, or the pump, and I'll go ahead and paste that here into my input section. And then I also need my output. Okay, so that's the level in tank 2, and that's going to be my measured value. And then if I just scroll down, you can see I can copy time in as well. If I just select those two and click the little black, double click on this black button, it'll fill down for me. Went up to 949 seconds. Okay, so let me go ahead and just have the model come down as well. Go ahead and predict over those values, and then also the sum of absolute value, and then also the squared values for my summation. Okay, and then I'm going to come back up here. There's my model prediction. Okay, this is a nonlinear process. You can see the manipulated variable and the controlled variable and the measured variable. And let's go ahead and minimize the sum of absolute errors again. Okay, so I'm going to go and use the solver again. Everything's filled in, and I'll go ahead and click solve and keep the solver solution. So, you know, there's some didn't fit perfectly. Let's go back and see what parameters it came up with. Okay, so a little bit shorter time constant, and also the gain was a little bit less as well. Okay, so you can clearly see this is a nonlinear process. Let me go paste these back into my results file, and this was for the doublet test, and KP equals that, and then tau P equals 104. Okay, so a little bit different time constant and gain for the doublet test. So one thing interesting to point out is this was the graphical method. Okay, we used a graphical method first, and then we used the optimization method for both of these as well. So for anything other than a simple step test, it's kind of difficult to use a graphical method to obtain your model. We most often try to use optimization methods because it allows us flexibility to give different input signals. Okay, so we've got these. One of the things that we can do is go get an IMC or an ITAE correlation. What we're going to do is go ahead and go back to our back to our course website here. If you go back to syllabus, you can see right down here there's a PDF for the practical process control textbook, and so I'm just going to search for ITAE. Okay, so if I search for that, here is my this is ITAE, so this is going to be for set point tracking. Then there's also a regulatory control for disturbance. So if you always have the same set point, you're going to use this one. If you're going to be changing the set point, then you'd use this one. So you can see a problem here. This one is going to be 0, okay, on the theta, because we estimated a dead time of 0. We can maybe just put in 1 second there just to make it so it isn't 0, or we can also look at the IMC tuning rules. The one rule that I like to use just in obtaining KC, which is my controller gain, is it's often fairly close to just 1 divided by KP. That's just a simple tuning rule, and we might use that in this case. Okay, so KC, here's my ITAE. Let's look for my IMC. Okay, internal model control correlations, and I think they're actually in the back of the very bottom of the book. Okay, but if I just search for that, here is the PI correlations. Okay, so let's see if we have any proportional only correlations for IMC. I'm going to go all the way to the end of the textbook here and just see what we can find. Okay, here are some tuning as DMC tuning correlations. Let me just scroll up a little bit. I believe they're in one of these appendices here. Wow, okay, that's maybe I'm not finding it. I thought I scrolled right past it. I'm going to go right above the index. Okay, I think this is it right here. Okay, so here's the IMC tuning. This is Appendix D2, and what I'm going to do is go ahead and go down. P only control for IMC is 1 divided by KP theta P, and this is actually a Ziegler-Nichols reaction curve, as no P only IMC exists. Okay, so we'll go ahead and use a Ziegler-Nichols correlation, and if that is 1 second, then KP would just be 1 divided by KP. Okay, so let's use 1 divided by KP for our controller, and actually let's go back and just see if there were any other things that we needed to answer for this problem that we had in the homework. Okay, so I'm going to go back to the homework. Let me open up special problem 3 and scroll down. Okay, so we used Excel to optimize them. Are they the same? I'd prefer to use the optimized values. Okay, so we did the doublet test, and then let's go ahead and put in a P-only controller to this system. Okay, so what I'm going to do is I'm just going to say that KC, my controller gain, is about 1 divided by KP. Okay, so that's going to be 1 divided by about 1.4, okay, 1.43. It was a little bit less for the doublet test, so maybe we'll just compromise there, about 1.3. Okay, so let me get out the Excel, and 1 divided by 1.3, 0.77. Okay, so about 0.777. Okay, so that'll be our controller gain that we'll use. So let me go back to the Simulink. Okay, so now I'm going to go back to the Simulink and go ahead and add a PID controller. Now that we have our tuning constant for P only, and so what I'm going to do is go ahead and view library browser. Go ahead and open that up, and then select PID, and then drag that in here. I'm just going to put that over here. So instead of the pump output being manually controlled, we're just going to go ahead and delete that. Okay, this is the blue box is just a slider control. You could put a constant in there. And then what I'm going to do is go ahead and just link this up to the output is then going to take the place of that pump, the pump output. And then what's going to be coming in is going to be the difference between the set point and the measured value. Okay, so I'm going to have a sum here as well. Go ahead and drag that over, and then go ahead and put the sum here, and let me move this over just a little bit more. Okay, and then what I'm going to do is go ahead and right click that, bring it off. I need to go ahead and make that a negative sign just so I subtract. I'm going to go ahead and subtract, there we go, the measured value. Now if you just follow the signals that are coming out, the tank dynamics, what's coming in here is a valve position and then also a pump output. Okay, the pump is coming into the tank dynamics model. This is simulating the tank. There's a gain multiplier, and then this is the this signal right here. These are the heights. Okay, so this plots the tank. This is a set point. This is the these are the two heights of the tank, and I split those out here. The second one is actually the height of the second tank. And what I'm going to do is go ahead and just bring that out here and go ahead and bring that into the negative sign, and then have my PID controller here. Okay, so what this is going to be doing, this proportional only controller, I'm going to go ahead and open this up, and you'll see what type of controller you want. You can select P only if you want, and then it'll just reduce it down to that one parameter. Okay, so what I'm going to do is go ahead and add in, I think 0.77 is what we came up with, and click apply, and then let's go ahead and just simulate for 500 seconds. Okay, so what's going to happen is it's going to start filling up. It's going to be proportional to that air. I'm going to bring back my measured values here, and then also watch my tank. I just maximize that. Okay, so you're going to see some offset here, and that's just a characteristic of proportional only controller. It's going to, my set point is up here at 0.5, but it's going to linger here somewhere around 0.2. So first thing I'm going to do is go ahead and increase my gain. I might be able to make this just a little bit more aggressive. So I'm going to increase that to 5. Okay, and I'll just go ahead and stop it. And you can see it was really starting to take off there right at the end. Let me go ahead and go for 1,000, and as we're going I can just change that gain of my controller. Ooh, I just go in ahead and overfilled my tank. A little bit too aggressive there on my controller, so let me go ahead and just I'm going to go ahead and just reduce that. Okay, I went way too aggressive on my controller. Maybe I'll just double it to 1.4 instead of going all the way to 5. Okay, so let me go ahead and simulate that again, and you can see tank 1 is filling, and the important thing is that we don't want to overfill that tank, and we're going to be at an offset somewhere around here. Getting a little bit closer. I could go ahead and increase that some more. 3. Let me just see what that does. Okay, so it's going to increase it. My offset is going to decrease. Okay, so as I look at my measured levels, okay, so it's going to oscillate just a little bit here, and then it looks like it's going to level out. It might level out somewhere right in this area. Okay, so proportional only controller, there's often offset in a proportional only controller, and but you can tune it for applications like pressure control or sometimes a level control as well. Let's go ahead and just add in an integral term, just see what happens with this, just to see on this integral. It looks like can't change that while the simulation is going. So let me go ahead and just add that into the make this, instead of a P only controller, make it a PI controller, and I'm just going to use, let's just go back to the original value, 0.77, and then I'm going to do 1 divided by 1.4 times 142. That's just a ballpark there. 1 divided by the KP times tau p, and that's just a good place to start for integral term. That's just a simple tuning rule. It's not even ITAE or IMC tuning rules. I'm just going to go ahead and try that with PI control, and let's just see how that does. Now we should be able to get rid of this offset. It should eventually be able to reach that value. The integral term will continue to work on it and increase the level in tank 1 until it gets there. Okay, so what we're going to see is it's not going to level out at 0.2 or 0.35, but it should make it all the way to 0.5 eventually. Okay, so there's the level in tank 1 and level in tank 2, and we're about 25% of the way through. I'm going to go ahead and make this maybe just a little bit more aggressive. So maybe just multiply that by 2 on the integral, a little bit more integral action, and let's just see if that's getting there any more quickly. Okay, so it looks like it is getting there quickly. We'll just have to see how much overshoot we have on this simulation. Okay, so it looks like it is. This is the one that we're trying to get to 0.5. We don't want to overfill this. Make this one above 1.0. And if we also look at the pump as this is going, we can see what the controller is doing. So the controller is decreasing the pump level. Okay, and now it's going to increase it again and hopefully level off after a certain point. Okay, so let's go back to our measured levels one more time, and it looks like it's starting to oscillate. Maybe I did a little bit too much integral action there, and so it's going to start oscillating. And this is the process of tuning that you'll often use correlations to get you close, and then in simulation you can go through and just verify that your changes that you're making that it's going to work in simulation, and then implement those in practice as well. Okay, so this is almost done here. We'll see if that's able to level off on the tank levels, and it looks like it's getting pretty close to our set point. So it looks like we have a fairly well tuned response. We'll go ahead and bring up the plot just at the end just to verify that it worked well. And it looked like it made it up to our set point. Okay, so let me just go ahead and summarize what we did for this. We went through this problem, and we first of all used graphical methods to obtain Kp, Tau p, and Theta p, the three constants from our first order plus dead time model. And then we also did that in Excel. We went ahead and optimized that. And then we also used a doublet test and then fit a first order plus dead time. Doublets are good, especially if you have a nonlinear process. You can sample above and below the nominal values. We use some tuning rules. You could use ITAE or IMC to do that. And then we got our proportional only controller, and then implemented that proportional only. We also went a little step ahead and did a PI controller as well, and then just tuned it, adjusted up or down until an acceptable response was achieved. Okay, so that's it for special problem 3. You'll visit the course website here for more problems and additional information on process control.